Right, well, good morning, ladies and gentlemen. Welcome to this year's Orkney Science Festival 2025. My name is Eric Walker, and it's my pleasure to be hosting the second talk of the festival in the Picky. My knowledge and understanding of quantum science is growing, I can assure you that. Mind you, it starts from a very, very low base level. And I was reminded of how little I actually did know about it after hosting the first talk this morning. But I'm getting there. Now, before we start, we need to go over some housekeeping. There are no planned fire drills today. The fire alarms are tested weekly, but this won't happen at this event, so if you do hear a fire alarm, it is for real. There are 3 fire exits. There are 2 fire exits down here, just go straight through the doors, and the 3rd fire exit is at the top where you've just come in. So if you hear the fire alarm, just make your way smartly out, and if you can assemble in the car park and wait until you're instructed to come back into the building via the main entrance. Now, someone else, could you please put your mobiles into silent mode or aircraft mode? That'll stop them going off. I've just checked mine so I don't embarrass myself after giving the instruction and then I'm the perpetrator. And just to prepare you all, there will be a roving mic going around at the end of Andrew's talk to capture any questions that you will likely have for him. So just to get you into that mindset. So today, our speaker this morning is Professor Andrew Briggs of the University of Oxford. Andrew is the Emeritus Professor of Nanomaterials at the University of Oxford and is the Executive Chair of a company called Controlox. Andrew is also a pilot. And Andrew flew himself here via a stopover at Wick. So we might make it more challenging for you next year and ask you to cycle it. That's a good cycle for you. Andrew's research interests focus on nanomaterials for quantum technologies and the thermodynamics of timekeeping and learning. In 2021, he co-founded Controlox to commercialize machine learning for tuning and characterizing quantum devices with performance that exceeds what is feasible for humans and greatly accelerates the progress in quantum computing. He has over 650 publications, and these have been cited more than 31,500 times. So very relevant work. He's written books for general readership, which include The Penultimate Curiosity, for which there's a documentary film and a 6-book series for children. So this sounds like it could be pitched at my level, which is good.
And there's also a session on that on Saturday afternoon.
There's a session on that on Saturday afternoon. So there you go. There's a good bit of marketing.
Yeah, it's the tea and philosophy session.
Ah, cool. Right, that might be it, that then. Today, Andrew's going to tell us about an entirely different type of computing, which we're told will make it possible to do things that have never been done before. How does it work? What are the dangers? When will it arrive? Andrew, over to you.
Well, thank you very much, Eric, for that kind introduction. I feel after an introduction like that, I can scarcely wait to hear myself speak. How many people were here for Professor Millen's talk just before the coffee break? Raise a hand. Okay, that's great. One person was heard coming out of that talk saying, well, I'm still confused, but at a deeper level. So, last Thursday, there was a debate in the Union Society at the University of Oxford. So the Union Society, you have to imagine a building, a 19th century building, and therefore with a gallery around the main part and the central area, and a very large dais with a chair for the president of the discussion to sit on. And that building, the Oxford Union, has probably seen more prime ministers and other heads of state come out of it than any other building in the world, probably. But the debate last Thursday was not about politics, it was about quantum computing. And the motion, what happens is they discuss a motion, and then when the discussion and the debate is ended, people can leave through one of two doors, the eyes and the nose, rather like Westminster. And the motion that was being discussed was this House believes that quantum computers will have a greater impact on our lives than conventional ones. Now, you may know a bit more about it by the end of this morning's session, but from what you already know, from what James said and what James told you about the quantum world, I'd like you to raise a hand to show which door you'd go through. So that was I'll tell you the motion. Then first of all, I'll ask you to raise a hand if you were the eyes, and second, raise a hand if you would have gone out through the nose door. The motion was, this House believes that quantum computers will have a greater impact on our lives than conventional ones. So if after the debate you would have gone out through the eyes door, please raise a hand now. Okay, and if you would have gone out through the nose door, please raise a hand now. Very interesting. At Oxford, it was the other way. I think here the eyes have it. At Oxford, it was the other way around. The nose had it. So 72 people voted aye and 94 noes. And over lunch, you can discuss, what you might vote now in the light of what I'm about to tell you. So, why might quantum be interesting? Well, quantum computers play by different rules, the rules of the quantum mechanics that was the subject of the last session. And they'll make certain calculations possible that would simply not be feasible on classical high-performance computing. And basically, those problems fall into two categories. One is what's called analog quantum simulation, where you're trying to use a quantum system as an analogy of some quantum problem you've got. And the other one is digital quantum processing, where you have gates rather like you do in a classical computer, except that, as we'll see in a moment, they're different. And in 2022, the Nobel Prize for Physics went to Alan Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, which established the violation of Bell's inequalities and pioneering quantum information science. Quantum information science embraces many things like sensors and so on and so forth, but the flagship technology to arrive from quantum information science is quantum computing. And Eric mentioned my own company, Quantrolox, where, like the rest of the world, we're celebrating the International Year of Quantum Science and Technology. And the software that Quantrolox licenses for tuning and characterizing quantum devices is greatly accelerating the progress that the field is making. Now, before I go on to tell you a bit more about what quantum computing is, let me just give you a sense of the impact that it's going to have. So this is taken from a report by the McKinsey Consulting Company, and they reckon that by the year 2035, in other words, 10 years from now, the potential economic value from quantum computing will be somewhere between $900 billion and $2 trillion. And the particular companies that are building the quantum computers, they're reckoning that the revenue this year is likely to exceed $1 billion. So this is the sort of scale of the impact that we're talking about. And you can get some sense of what investors believe from the investments that are being made for quantum technology startups. Last year, it nearly doubled to $2 billion last year from $1.3 billion 2 years ago. And they're reckoning that government investment this year has already exceeded $10 billion, driven in part by a $7.4 billion investment in Japan. So this is something that's really going to make a difference to the world as it goes forward. And you've already had this wonderful summary of the rise of quantum computing with some of the figures that were mentioned in the previous talk. The one on the top left-hand corner is Erwin Schrödinger. And in the 1930s, he lived in the same street that my wife Diana and I live in now, in Northmoor Road in Oxford. We live in number 5, he lived in number 24. And while he was there, he devised the concept of Verschränkung, which is often translated as entanglement. But if you want to think of entanglement, if I was German, I would describe my arms as verschränken, if I were like that. And he also came up with this thought experiment about a cat that was simultaneously dead and alive. How many people have heard of Schrödinger's cat? So some of you have. You may have seen this cartoon of the Schrödingers at the vet, where they'd take, the cat was called Milton, incidentally. He had it when he lived in 24 Northmoor Road. And here's the vet talking to Erwin Schrödinger and saying, "About your cat, Mr. Schrödinger, I have good news and bad news." So let's come to what quantum information is. And classical digital processing, the sort of processing that goes into all the information in your phone and your laptop and all your communications and so on, comes in bits. So it comes in zeros. Each bit is either a 0 or a 1. And woe betide you if it's anywhere in between. You want it to be either a 0 or a 1. Quantum information, the first difference is that the quantum information comes in bits, or quantum bits we call them, qubits, that are simultaneously a 0 and a 1. And the best way to visualize that is to think of a globe of the Earth. So here's a globe of the Earth, all right? England here somewhere, Orkney up here somewhere. The North Pole represents a 0 conventionally, and the South Pole represents a 1. So your classical information is either at the North Pole or it's at the South Pole. Now the quantum information is not somewhere along the axis of the globe. If it were, it would be useless. It's called a mixed state then. The useful quantum information is on the surface of the globe. And to describe somewhere on the surface of the globe, you've got to have two parameters. The first one is how far north-south it is, and we call that the latitude. And the second one is how far east-west it is, and we call that the longitude. And in quantum information, you see something that was both, supposing it was an equal amount of 0 and 1, it would be on the equator. But Nairobi and Singapore, although they're both on the equator, are not the same place because they have different longitude. And it's this combination of both latitude and longitude that gives quantum superposition its amazing power. And then once you've got your head around this concept that quantum information is like being on the surface of a sphere. In science, it's called the Bloch sphere, but you can think of it as a globe of the Earth. You've then got various properties that come from that. The first one is superposition, which we've been talking about. And the next one is the entanglement that James was beginning to explain to you earlier on, although explain is perhaps too strong a word. At least describe it, all right? And then there's a further possibility that is brought about by quantum computing, and that is quantum parallelism. That is to say that if I've got one qubit that's simultaneously a 0 and a 1, I can be doing two calculations at the same time, one on the 0 and one on the 1. If I've got two of them, I can be doing 4 calculations at the same time. Okay, 0, 0, 0, 1, 1, 0, and 1, 1, all right? If I've got 3 of them, I can be doing 8, and so on. If I've got 10, I can be doing over 1,000. So it's these 3 properties that give quantum computing its spectacular potential. Now let's think of those 2 kinds of quantum computing that I was talking about. The first one is simulation. And in the early 80s, Richard Feynman, the Nobel-winning physicist. Anybody here grew up with the Feynman lectures on physics? Yeah, so you know who I'm talking about. Okay, he said in a very important lecture there, nature isn't classical. And if you want to make a simulation of nature, you'd better make it quantum mechanical. And by golly, it's a wonderful problem because it doesn't look so easy. And that was one of the thoughts that drove the development of quantum computing, the prospect of being able to simulate complex systems on a controlled computer. The other one is quantum logic, and those properties of superposition and entanglement and quantum parallelism give you whole new possibilities in computing that are not open to you in a classical computer. So let's think of some logic you can do, all right? So if you're doing classical logic, you can have a not operation. So not 1 is 0. Not true is false. And if you do it twice, you get back to where you started. So not true is true. Not 1 is 1. But in classical logic, there's no operation which, if you do it twice, becomes a not operation. So you can't have what might be called a square root of not operation. But in quantum computing, you can have a square root of a not operation. You can have an operation which, if you do it twice, is not. And you can see why in terms of my globe. That if I'm starting at the North Pole and I move through 90 degrees, I get to a superposition state. And if I move another 90 degrees, I get down to the South Pole. So my 90-degree rotation has become a square root of not operation. So this opens some new possibilities to us. And then the entanglement, and you see the square root of not applied to a 0 is just a superposition state. That's how it works. And that's done routinely in every quantum computing lab in the world daily. Now you can think of the swap operation. So if I have a swap operation, I can do a swap. And if I do it twice, I get back to where I started. But in classical logic, there's no way you can have a square root of not operation, because this doesn't really exist. I haven't swapped them yet, okay? So I have to do a complete swap operation. But in quantum computing, you can have a square root of swap, and it's called entanglement. So if I take two distinct states and entangle them, I've done a square root of swap. And if I do the same operation again, I get a complete swap operation. And again, that's done routinely. And now finally, you've got this amazing possibility of exponential scale-up. So if I've got 1 qubit, I can do a certain amount of computing power. If I want to double the computing power, I add a qubit. If I want 10 times the computing power, I add 10 more qubits. So supposing I provide you with a quantum computer on Monday, and on Tuesday you come to me and you say, oh, Professor Briggs, that quantum computer you gave me isn't nearly powerful enough. I want one that's 1,000 times more powerful, please. I say, well, that's fine. We'll add 10 more qubits, and you've got 1,000 times the computing power. And then on Wednesday, you come to me and say, no, I've thought again. I didn't want one that's 1,000 times more powerful. I want one that's 1 billion times more powerful. And I said, well, that's fine. We just add 30 qubits, and you get that exponential capacity in the computing. So I hope you can begin to see why people get so excited about this. But now you say, well, you know, if it's all so clever, how come we aren't all using them at the moment? And the main problem, there are lots of answers to that question, the main problem is that these qubits are very, very fragile. They're very susceptible to corruption, in particular in a form called decoherence. And so the errors creep in, you might think, faster than you can cope with them. In conventional computers, we also have errors. So your computers in your phone are making mistakes the whole time, and error correction is introduced, and it works well. And the way that the errors are corrected in conventional computing is you have what's called a fan-out operation. So you make several copies of the information, and then you compare the copies. And I don't know if any of you have ever been in the cockpit of a sort of old four-engine plane. And what you would have reaching up over the pilots' heads would be a whole row, a whole series of instruments, and there'd be four instruments to each row, one for each engine. And it would be too complicated for the pilot to have to know what each instrument's supposed to be saying. That's too difficult. But you can look at them and you can make sure that for each engine, for each instrument, all four of them are saying roughly the same thing. And if you notice that one of the instruments is pointing somewhere quite different, you think, I better investigate and see what's up there. And that's roughly how error correction works in conventional information. So why can't we do it in quantum computing? And the reason is that there's a theorem of quantum mechanics which is called the no-cloning theorem, which basically says it's not possible to photocopy quantum information. You can't do it. And therefore, you can't have a fan-out operation. You can't just make lots of copies that you compare with each other. That's forbidden. For many years, it was thought that this would be a complete showstopper in quantum computing, that the combination of the fragility of the quantum states and the no-cloning theorem, which says you can't copy them, would prevent you doing error correction, therefore it would prevent useful quantum computing came along. And one of the people who found a very clever way around this was a colleague at Oxford called Andrew Steen. Andrew and I have written a book together. It's called It Keeps Me Seeking, and there'll be some copies available at the bookshop in town after I deliver them this afternoon. And Andrew came up with a clever way of doing fault-tolerant error correction, which overcame this problem. So the reason that it's difficult is because of the no-cloning theorem. For many years, people tried to think, well, what could we use quantum computers for anyway, even though they're vulnerable to errors? And that was an era called noisy intermediate scale quantum. It was trying to find uses for quantum computers that did not require error correction. And by and large, there are still some people doing it. By and large, that's a fad that's sort of passed. So then, based on the work of Andrew Steen and others, people came up with fault-tolerant error correction. And there are various ways of doing it. You can use surface codes. You can use something called a low-density parity check. But one of the problems with this is that there's quite a big overhead. You need quite a big redundancy because you make a syndrome of, well, you make a whole cluster of states and you measure a syndrome across the states. But it works and great progress is being made. And so as a result of this, the sort of thing people look at when they're evaluating candidate technologies for building quantum computers is, first of all, the number of qubits, because as I've said, the more you can have, you get this exponential increase in the power. But then because you need a redundancy in order to do error correction, people distinguish between the number of physical qubits, which is the number you've made, and then because of the overhead, the number of logical qubits. In other words, how many logical states can you actually make use of? They care about the fidelity. So if you have an operation and you think you've done it to a single qubit, how faithful is it? And I can tell you now that the sort of rule of thumb is that unless you've got at least 99% fidelity, you're not really in the market. In fact, you can be rather mischievous and call it the infidelity and say that the infidelity has got to be less than 1%. In fact, people are doing, they're getting 99.99%, and some hero experiments are getting 5 nines fidelity. And then you want to know how well you can do it for a 2-qubit gate. That would be with entangled states. And then another thing that people think about a lot is the T1 time. That's how long does it remember what its latitude should be on the Bloch sphere. And then the T2 time is how long does it remember what its longitude should be on the Bloch sphere. And generally speaking, it's harder to remember the longitude than the latitude. And then people worry about the gate speed. How fast can you do a gate? And you can imagine you want the gate speed to be much faster than the T1 and T2 times, because you want to do gates before it forgets what its state should be. So those are the sort of vital statistics you'll be looking for. And if you're making a quantum computer, you need a whole stack of different components. Up at the top is the application, the equivalent of the app on your phone. And then there's the quantum algorithms that'll implement that app. And then there's the application-specific interface and the cloud access. Then you've got to have a compiler. And then you've got to control the qubits. That's where my company comes in, the Quantilock software for controlling it. And then you've got the qubits themselves. And it's those qubits is actually the only bit that's quantum mechanical in the whole thing. All the rest is just classical electronics, classical instrumentation, and classical software. And then sometimes, depending on what the qubits are made of, you may need an environment for them. It may have to be a vacuum, or it may have to be a low-temperature cryostat. So those are the sort of things that you need. And most people, when they're thinking about quantum computing at this level, and what I'm going to concentrate on is this, where's it gone? The physical qubit hardware here, this bottom layer, the actual thing you're making the qubit out of. So now I'm going to just tell you some of the ways that people are trying to build these quantum computers. And there are many different ways. From about a quarter of a century ago, I became director of the first coordinated national effort in quantum information processing. And people would ask me which of the candidate implementations that were being talked about did I think would dominate. And I said, well, I think it's too early to say. We'll have to see how they get on, you see. 25 years later, I still think it's too early to say, and so do other people. This is the result of a survey that's conducted each year by a colleague who was in Oxford, now in Canada, called Michel Mosca. And what he does is he takes about 35 experts around the world, 30 or so, and he asks their opinion about various aspects of quantum computing. And we'll come to another of these charts later on. And on the left-hand side are some of the candidate implementations, and I'll go through the first 5 of those in a moment. But when you look at this, the first thing you'll see is that there's no consensus. There's no agreement, even amongst well-qualified and knowledgeable experts, about which of those dominates. And even the one that's at the top of the list, the superconducting systems, only 11 out of whatever it was, about 30 people, 30 or so people, less than half of them would say that even that one is the lead candidate. So there's still scope for a range of opinions. And my own feeling about this is the following. The reason I think it's still too early to say is not because of problems that any of them has encountered, but because each of these candidate implementations keeps having successes. And I keep reading of new breakthroughs, or friends tell me about them, or I read about them, or whatever. And so because each of the candidate implementations keeps making significant advances, I still think it's too early to say which will dominate, and who knows whether any of them will. Maybe several of them will continue to be used for a long time. So I'll just tell you what the different implementations are in this list. So if you want to start making a quantum computer in your garden shed after this talk, you can go back and think which of these you'd like to do. One of them is superconducting systems. This is a chip made by a company called Quantware. All superconducting systems have to work in a low-temperature environment, and the way to create it is to have a dilution refrigerator, which works by diluting helium-3 in helium-4. And when these dilution fridges are open, they're all gold-plated inside, so they look terribly shiny and smart. But that's actually no use if you're trying to do an experiment. that's when it's open and you're changing something or mending something or whatever, or installing something. What you want to see is a grey, dull can over it, so you can't see any of the shiny gold, and then the thing's actually working. But I'm afraid we're all guilty of this, of using the photogenic, shiny qualities. Even I've been known to do it. Here's what one of the chips looks like. That one on the left is actually from a research lab in Zurich. Andreas Wallraff, and then when it's packaged up, it might look like the picture on the right. Here's a roadmap from an Oxford spin-out company called Oxford Quantum Circuits, and you can begin to see now how you look at these vital statistics, you see. So if you look at what they're hoping to achieve within the next 9 years, and that's a timescale that's probably realistic, they're hoping by then that they might have 50,000 logical qubits. And remember, because of the overhead, they're going to need many more than 50,000 physical qubits in order to achieve that. They're hoping to have an error rate less than 10 to the minus 12, and that's, of course, with full error correction. And then they're hoping to have a clock speed of 10 megahertz, and so on. And they hope they can make all of this on a 12-inch wafer. So that's superconducting, and they're making great progress. And if you saw the news yesterday, there's a Finnish company that makes superconducting qubits, which yesterday announced another $350 million of funding for developing their qubits. So that gives you a scale of the confidence of investors. Also reminds you, if you're trying to make one of these in your garden shed, you'd better have a budget of about $350 million in order to do it, because these are expensive experiments. One of the earliest ways to try to do them was with trapped ions. These are atoms where you've added an electron, or in the case of the trapped ions, you've subtracted an electron, so they've got an electric charge, and you want to try to track them in an electrostatic field. And that's difficult because of some equations developed by a Scotsman called James Clerk Maxwell, who worked out the equations that govern electric fields. And it's not possible to have an electric field that would confine a charged particle in all three directions. So the way they get around this is to have a rotating field. And a way of thinking about it is this. Supposing you've got the saddle of a horse, and you're trying to balance a ball on the saddle of the horse, all right? So you can try and find exactly the point where it's flat and hope that it'll stay there. But of course, if there's the slightest jiggle, it'll fall off to one side or the other. So you get around that by spinning the saddle round. So now you imagine the ball that's on the saddle point there, and it's spinning round, so maybe it starts to fall off in one direction. But before it can fall very far, the saddle has rotated 90 degrees, and now it's trying to fall uphill, so it's going to be pulled back to the middle. So you make these ion traps by having spinning electrostatic saddles, if you like. And they have very high fidelity. There was huge technology before quantum computing came along, because they're the basis of the atomic clocks that give us our atomic timekeeping. So there was a lot known about them well in advance. This was an experiment from a colleague at Oxford. Actually, it's the lab that was created by Andrew Steen, who I mentioned earlier, now taken over by David Lucas. And so they're making very successful breakthroughs in quantum computing in ion traps. And a few weeks ago, there was this announcement here that the Oxford spin-out company called Oxford Ionics was acquired by an American company called IonQ, and they valued the Oxford spin-out company at $1.1 billion. So that's the sort of value that's being created in this field. And there's their roadmap. And again, you're beginning to get a sense of what to look for here. They reckon they're going to have, by 2030, so within the next 5 years, they're hoping to have 2 million physical qubits, from which they hope to be able to derive 80,000 logical qubits, and they're hoping for an error rate of less than 10 to the minus 12 also. And So that's what the ion traps are looking like. Then you can try doing it just with straight photons. We were thinking earlier how we think of the quantum nature of light, that photons you can think of as particles and you can think of as waves. This is from a Chinese laboratory. So don't forget the Chinese in this race to build a quantum computing. McKinsey estimate that the Chinese have had more investment from the government than any other country in the world. The figures put at 15 billion, and it's run by a brilliant scientist called Yanwei Pan, who spent 12 years in Austria with some of the top people in the world, including Anton Zeilinger, whose picture you saw earlier in the gallery of Nobel laureates. And we'll later come to why people want to build quantum computers. The Americans would like to have the first one. In fact, they'd like to have the only one. But the Chinese are very good at it and making great progress. This is the sort of wafer that an optical quantum computer might be made on. This one's from a company that, it originally came from Bristol, called Psi Quantum. And they've now got massive investments in Australia and in Chicago. Another way of making a quantum computer is with neutral atoms. So this is not like the charged atoms, the ions that I mentioned earlier. These are neutral atoms. And until about 5 years ago, it was thought they would only be suitable for simulations. And then some clever steps were made with some excited states and Rydberg states, and people realized you could also use them for gate quantum computing, for doing logical operations. And the way you do those, you can't confine them electrostatically, but what you do is you use laser beams to produce regions of confinement, and it's a bit like making a sort of optical egg tray. Can you imagine an egg tray where you can fit one egg into each slot in the egg tray? It's a bit like that with atoms. So here's a sort of scheme of what it might look like. That's what it looks like in the laboratory. This is a company that's based partly in Oxford called Inflection. And so that's the sort of laboratory experiment. And this is their vision for what it'll look like when they can actually build it in an integrated way. And here is their roadmap. And we're beginning to know what numbers to look for, aren't we? We're looking for more than 10,000 physical qubits by their fourth generation, and they think they'll have 100 logical qubits. And you notice those numbers are rather small compared with the other ones I gave. And then another way of doing quantum computers is to use the same materials that we use for the computers in your phone, namely silicon chips. And there we do it by having electron spins in silicon. Here's an example of one that was made actually in the Netherlands, in Delft. And each of these is a qubit with electrodes to control them. And if you could make a quantum computer of silicon, you'd have this fantastic benefit that you can use all the silicon processing industry that's taken 50 years or more to develop, and you could use those for building your quantum computer. That's what gets people excited. But the limitation is this: people have been working at this since the late 90s, and they're quite proud of a device that has 6 qubits in it. So it's proved a long, hard journey, and it's taking a lot of time and effort to make it in a scalable form. Here's another one from a silicon foundry. And this just gives you a sense of the great variety of ways that you could make them in silicon. The left-hand picture is from an Oxford spin-out company called Quantum Motion, actually one of my former students, who's now a professor at UCL. And that's basically using the same CMOS that you use in the computer in your phone. The right-hand side is actually from a company from another of my students, Steph Simmons, who's now at Simon Fraser University in Vancouver in Canada. And she has this rather clever way of making defect centers in silicon, which consist of 2 carbon atoms and 1 hydrogen atom. And she can make qubits that way. So that gives you an overview of the 5 main ways that people are trying to make quantum computers. And in my view, each of them is still, a serious contender. So we'll watch this space and see what happens. Well, now, in order to, what's another big technology development that's getting massive investment at the moment? That, of course, is AI. So what is the relationship between AI and quantum computing? And basically, it's a two-way relationship, which is illustrated by this slide here from McKinsey. And on the left-hand side, they're talking about how quantum computing can help with generative AI. And on the right-hand side of the diagram, they're talking about how generative AI might speed up the development of quantum computing hardware and software. And it's the second of those that my company does. And in fact, this is a slide of results from my laboratory at Oxford University, but it's all of a piece. And this is an amazing doctoral project from a student called Jonas Schuff, which he completed, where he identifies 4 different stages in the tuning and characterizing of one of these qubits. And he uses actually different methods of AI at each stage. So AI is not one method, it's a whole discipline of methods. And the software has a rather clever sort of decision tree. So it starts off over here where you've just put the device into the cryostat. This is particular implementation was for spins in silicon. And the software tries one way of tuning them up. And it chunters along here, and did that work? Yeah, it seems to work well. Let's keep going. Chunters along here. Oh, that seemed to work well. Oh dear, it doesn't seem to be getting any further. So the software goes back in the tree to this branch point and says, well, I'm going to try a different way. Let's try this. Oh, that works quite well. Let's try, oh, that got stuck, that didn't work. Let's try this one. Oh, that got stuck, that didn't work. So it goes all the way back there and tries different possibilities until eventually it finds one possibility that leads to a tunable, workable qubit. So that's an illustration of the way that AI is being used for developing quantum computing. But again, as I've said, this can be a two-way process. So artificial intelligence can help quantum computing, but quantum computing can also help artificial intelligence. And this next slide is actually the work of another of my former students, Anna Pearson, who now works for a quantum computing company called Quantinuum. And this is the first implementation I've seen of a quantum computer doing the sort of learning that a large language model could do. Except this is not a large language model, it's a very small language model because the quantum computers at the moment are very small. But what it does is it can take natural language. Bob walks west, Alice walks north, John walks south, Alice turns right, John turns left, Bob follows Alice, Bob goes in the opposite direction of John. I hope you're following this. And now you say, well, now where is each of them, or something like that. So the computer can follow this natural language in a quantum computer and work out answers to the sort of questions that you might ask as a result. So it's just early beginnings. It's very tiny baby steps, but it's important baby steps. So that's the sort of thing that Anna's doing. And this is just a graph of the success rate. Well, now, when is all this going to be ready? When are we going to be able to use quantum computers and actually benefit from all these amazing capacities that I've been telling you about? And again, there's a range of opinions, and you won't find a complete consensus as to what the answers are. But in a moment, I'll show you another result from the survey of Michel Mosca to show you what some of the experts are thinking. And you'll see there's a range of views. And the particular question that I'm going to show you the statistics of the answers to was, when will a quantum computer be able to crack an RSA code in 24 hours? Now, the RSA code is basically how all information is encrypted nowadays. whether it's government secrets, whether it's military intelligence, or whether it's you just paying for something on your iPhone that you've bought on the internet and it's encrypting your credit card details. And the RSA code works on the basis of the fact that there's certain mathematical operations which are very easy to do one way and very hard to do in reverse. So let's think of a simple example. I'm going to give you two prime numbers and ask you to multiply them together. So two prime numbers are 11 and 97. Who can multiply 11 by 97 in their head? Who's going to come up with the answer? You're not allowed to use your phone. 11 times 97. Yes? Pardon?
1057.
1057. Any advance on 1057?
1067.
Sorry? Thank you. Okay. Well, perhaps that's what you said. Maybe I misheard. Right. Now, here's another one. I'm going to give you the product of two prime numbers. What are the prime numbers? 899. What are the factors of 899? It's a smaller number than the one you've just had. Anybody get it? Yes? Yes.
51 and 29.
Thank you so much. It's a particularly easy case because it's the difference of two squares, isn't it? It's 30 squared minus 1 squared, all right? So you can see the trick. The point is that factorizing the product of two large prime numbers is so hard that it provides a secure basis for all the cryptography that's done in the world, or almost all of it, all right? A quantum computer can factorize products of primes using something called a quantum Fourier transform. And this became clear in the 1990s. And since then, well, the Americans wanted to have the first computer that would factorize products of large prime numbers so that they could cryptanalyze all security messages around the world. And as I said, they wanted to have the only one so that the Chinese couldn't do it, or the Russians, or anybody else. And so this is a survey of when people think a quantum computer will be able to break a particular RSA code in 24 hours, all right? And again, you see there's a spread of opinions. But if you look at the sort of 50% probability, it's tending to hover around 15 years or so. It's something of what it's looking like, okay? Now, this is a particularly hard task for quantum computers, and there may be applications that come much earlier. And of course, you can imagine all these companies getting all this investment for quantum computing are promising things on much sooner timescales than that. So who knows, they may succeed. You know, maybe we'll be using useful quantum computers in 5 years' time. But you know, there's some uncertainty attached to that. So the promise of quantum computing, just to sort of summarize, you know, when will it usefully be available? I've just shown you a survey of that, maybe 5 years, maybe 15 years. What platform will dominate? Too early to say. What applications will succeed? People are working very hard on that. I haven't talked much about that this morning, but again, it's almost too early to see. But the expectations are very clear. First of all, the underlying quantum physics is very well established, both in theory and increasingly in experiment. And when it comes along, because of this amazing exponential power, it could be utterly disruptive, even if it had no other applications than code breaking. Think of the disruption that would cause. And actually, I think that will not prove to be the most significant application. I think there'll be other more important ones. And last of all, and I'll be talking more about this on Saturday afternoon if you want to come then, that now is the time to be thinking about putting ethical guardrails in place for some of the candidate applications like drug discovery and code breaking and optimization, AI. And if I had much more time, I'd tell you about the ways that we've been much too slow and much too late in putting ethical guardrails in place for the uses of AI. It's been a human disaster, in my opinion. And what I long for and encourage my colleagues is let's not make the same mistake with the quantum computing. Let's think in plenty of time in advance what the ethical guardrails should be. And we have a group that considers this in Oxford as a dining club that meets for dinner the first Monday of every month. And one of the questions we found ourselves thinking, well, we want to implement values, and where do these values come from? And is there a moral reality there? And if so, are there values that are there to be discovered that we can implement and draw on when we're looking for ethical guardrails for quantum computing? Well, that's a lot to think about. Eric, over to you.
Oh, thank you very much. Thank you very much for a very thought-provoking talk, Andrew. George, is about to walk around with the roving mic. If you put your hands up, I'm sure there'll be quite a few questions coming up for Andrew. So just put your hand up and we'll get to you. I've got one to kick off with. That's do you see quantum computers working, on their own, to replacing classical?
Oh, what an excellent question, Eric. I'm so glad you asked that. And we will always need classical computers, even if it was only to drive the quantum computers. You saw that stack that I put there. But many people are thinking further than that a quantum computer, as we learn what it's best at, may be a component in high-performance computing. So there are a number of high-performance classical computing centers around the world, one in Edinburgh, there's one in Garching near Munich, the Leibniz Rechenzentrum, where they are, another one in India, in Pune, CDAC, where they've got often regional or even national high-performance computing, classical computing, and they're inserting these little baby toy quantum computers that we've got at the moment into them to try to see whether there are tasks that the high-performance computer could pass to the quantum processing unit that it will be good at and can do that bit of the calculation fast, but you use the rest of the computer for the rest of the computation.
Using the right tool for the job, basically.
Yeah.
An observation, RSA is being deprecated now for about 5 or 10 years.
I'm sorry, I'm having great difficulty hearing with this sound system.
Can you hear me? I can hear some echo.
Yeah, that's good.
Okay. RSA has been deprecated now for about 5 or 10 years, and there's better systems. But one of the comments that people make is, in 25 years' time, when we have these quantum computers, they'll now be able to decrypt all the data being used today. It's like having an open book, so nothing is basically secret. And that's where they're trying to move on from the RSA computing. That's just sort of looking ahead to the future. So an observation.
Absolutely. And there's a whole field now of what's called post-quantum cryptography. So there are sort of two ways that you can get around this problem. One is to use quantum communication. It's usually in the form of quantum key distribution. And that's provably secure because of the no-cloning theorem. So if somebody intercepts quantum secure communication, they disrupt it in a way that can be detected by the legitimate recipient. So it's provably secure, and it's one possible way of getting around this. But it would be phenomenally expensive to install all the infrastructure for doing that. The other way is, as you said, post-quantum classical computation, which is other methods apart from RSA that would be, as far as we know, And that's an important qualification. As far as we know, wouldn't be vulnerable to attack by a quantum computer. There's a new Australian centre just been announced. A friend of mine is involved in that. There was a competition 2 years ago run by NIST in the USA for people to come up with clever post-quantum cryptography solutions. And 4 winners were announced with great trumpeting and ceremony. The following week, somebody on their laptop in an afternoon cracked one of the 4 winning methods. So it's hard to do, but it's a very important endeavor.
There's an old phrase used in computing, garbage in equals garbage out. When it comes to AI, is it not really the case that all the AI intelligence, as you call it, is guided by the inputs rather than it's kind of the runaway intelligence of AI that is uncontrollable?
I love that question. It may one day apply to quantum computing. Not yet, because the quantum computers are there. And before too long, it may apply to things like the large language models, because the LLMs are training on all the digital information that's available on the web, and there's an enormous amount of it. And some of it they pay for. There's a website where you can look up which of your books have been pirated. The AI obviously doesn't want to hear what I'm about to say, where you can see which of your books have been pirated and are being harvested by, generative pre-trained transformers. And I looked up my books, and it had 20 entries for pirated copies of my books that the generative pre-trained transformers were crawling all over. As more and more of what's on the web has been generated by LLMs, as you say, there's a risk of it getting detached from reality. Because, we'd like to think that some of what we write is related to reality. That's what we'd like to think. But if more and more of it is generated by pre-trained transformers, it's a bit like in the Middle Ages, the bestiaries that they had. So long before printing was invented, if you wanted books of animals, you copied them from previous books of animals, all right? And the animals in the bestiaries corresponded less and less to anything you might actually see if you went out and looked for yourself. There's a real danger of that happening with generative AI. I think you're absolutely right.
This will have to be the last question.
How might ethical guardrails be put in place worldwide?
I wish I had a good answer to that question. I'm so glad you're asking it. Oh, what are you waving at? Oh, I have to stand back. I'm sorry. I wish I had a good answer to that question. I think it's got to be a societal endeavor. I think that society has got to, first of all, formulate a clear concept of what values lead to human flourishing. I've written a book on that. I put it up there. It's going to be available in the bookshop. So that's the first thing we've got to do. And are these values that we just make up and invent, or are they a description of some moral reality? That's another important question. And you're not going to get a 5-minute answer to that. It's got to be a societal engagement and a societal debate, and it's got to be a strong enough debate that governments take note of it in order for politicians to get re-elected, which is usually the only thing a politician cares about. And it's also got to be strong enough for the companies to care about it. And if politicians' only question is, how do I get re-elected? A company's only question might be, how do I make profits? So it's got to be a societal endeavor like that. Regulation has a part to play. So does education of our kids, and of the next generation. It's got to be a multifaceted societal endeavour like that. It's not simple, but I believe it's terribly urgent.
Right, well, thank you very much. I see we've run out of time, but there is an opportunity to be able to talk with Andrew in just a moment.
Well, thank you for chairing so beautifully.